All right, welcome back to Calculus. Today we're continuing our discussion of curve sketching. So basically, the instructions are to use all the tools of the chapter to graph this curve. Okay, so the first couple steps, I'm not really going to worry about step one, step two, step three, whatever. I wrote the steps, but I don't really care that much. We just need to do all the stuff. First several are algebra, the last several are calculus. So I will always look at the domain first, I suppose. So what's the domain of G? We have 3x over x squared minus 1. So notice the denominator is 0 when x is plus or minus 1. So we can say the domain of G is what? All real numbers except for negative 1 and positive 1, which is negative infinity to negative 1, union negative 1 to 1, union 1 to infinity. Now, specifically, we can talk about what happens at plus and minus 1. So the discontinuities, of course, but they are what? Well, at plus and minus 1, notice this is a rational function. So if the denominator is 0 at plus and minus 1, but the numerator is non-zero, then those will be vertical asymptotes. And notice that, okay, plus and minus 1 both make the denominator 0, but both make the numerator non-zero. 3 if x is 1, the numerator is 3, and if the x is negative 1, the numerator is negative 3. So in both cases, plus and minus 1 make the denominator 0, but make the numerator non-zero, which means x equal plus or minus 1 are vertical asymptotes. So that gives us a very good idea of what's going on just right off the bat. We have two vertical asymptotes. Okay, so that's important to see. Let's do other algebra. Let's find the y-intercept and the x-intercepts, if there are any. So let's see. To find the y-intercept, well, we evaluate g of 0. That is, you plug 0 in. Well, what's g of 0? That's 3 times 0 over 0 squared. Oh, not minus. Minus, it's plus. 0 squared. I guess it really doesn't matter because the top is 0. So regardless, our answer is 0. So what does that tell us? That tells us that 0, 0 is a y-intercept. Okay? Now what about x-intercepts? You can technically have an infinite number of x-intercepts. How do you solve that? Well, you solve g of x equals 0. So you kind of do the opposite. To find a y-intercept, you plug 0 in. To find an x-intercept, you set equal to 0 and solve. So let's see. We have what? 3x over x squared minus 1 equals 0. Okay, we've said this many, many times now. If you have a rational function set equal to 0, all you have to worry about is the numerator set equal to 0, and then solve. So divide both sides by 3, and you get x equals 0. What does this tell us? This tells us that 0, 0 is an x-intercept. Now, we already knew that. Why? Because there's the y-intercept. And the y-intercept is the origin, which means 0, 0. That's 0, 0 is always by default both an x-intercept and a y-intercept. Okay? And by the way, there's only one of those x-intercepts. So the x-intercept is the y-intercept, and there's only one of each. Okay? I suppose I shouldn't say always going to be one y-intercept. It's possible there's no y-intercept. It's also possible there's multiple y-intercepts if you have an implicitly defined function. But I'll say for this section, we're going to stick to explicitly defined functions. So for this section, I would say, unless I decide to be a little crazy and do an implicit function, for this section we're going to have explicit functions, which will only have one or no y-intercepts. So there's your intercepts and domain. I guess the last thing really to do algebraically is to look for symmetry. And remember, to look for symmetry, straight up algebra, what you do is you evaluate g of negative x. Okay? So g of negative x is what? Well, it's 3 times negative x over negative x squared minus 1, which of course is negative 3 over what? Well, negative x squared is the same as positive x squared. So we can rewrite like, oh, I messed my x. We can rewrite like so. Now, what do you notice about that? That's the original function with a negative sign out front. In other words, it's negative g of x. What does that tell us? If g of negative x equals negative g of x, hence g of x is what, even or odd? Odd. Why? Because g of negative x equals negative g of x. That is the definition, basically, of a function being odd. What does that mean? Origin symmetry. What is origin symmetry? It's like this. If a comma b, so like, I don't know, like 1 comma 2 is on the graph, that means that what? Negative 1 comma negative 2, so negative 1 comma negative 2 has to also be on the graph. That's what origin symmetry is, a function that's odd. Okay, so we'll keep that in mind when we start graphing. Okay, so I think that's it as far as algebra is concerned. If I think of anything else, we'll take care of it. So let's hop into the calculus. So let's look at our analysis of the first derivative. So f prime is what? Okay, well, quotient rule time, I suppose. We haven't done the quotient rule in a little while. So the derivative of the top function is 3 times the bottom function x squared minus 1 minus the derivative of the bottom function 2x times the top function 3x over the bottom function squared. So x squared minus 1 squared. Of course, we need to clean it up. And you know what? I called that f. Why did I call it? It's g prime. Okay. So the denominator we know is x squared minus 1 squared. Now the numerator, if we let's see, let's just distribute, so that's 3x squared minus 3. Then we have what? Minus 6x squared, or 2x times 3x with a negative sign out front. So if we clean this up a little further, we get what? Negative 3x squared minus 3 over x squared minus 1 squared. And I suppose if you wanted to factor a 3 out of the top, you could. Or, I mean, you could factor a 3 out, a negative 3 out. Then you could factor it even further. It does. I mean, usually it's fine. We'll leave it like that for the time. There's g prime. G prime. Okay, I'm going to box it off. I'll need to reference that several more times. Now, what do we want to do with that derivative? Well, we want to find critical values. First of all, notice that the only values for which g prime is not defined are, again, plus and minus 1, which are exactly the same places where the original function was not defined. So, of course, the function's derivative, there is no slope at the asymptotes, so there's no derivative there. You know, the derivative is undefined, literally, at the values of plus and minus 1, because those are asymptotes. And the derivative is defined elsewhere, so there's not going to be any cusps or vertical tangent lines that we have to worry about. So the only thing we have to do as far as critical values are concerned is to solve g prime equals 0. So we have negative 3x squared minus 3 over x squared minus 1 squared equals 0. Now, I've already said it once in this video, whenever you have a quotient set equal to 0, all you have to worry about is the numerator set equal to 0, because that's the only way that quotient can be 0, is if the numerator is 0. Okay, divide both sides by negative 3, and we get, oh, what do we get here? Interesting. If we divide both sides by negative 3, we get x squared plus 1, yeah? Okay, and then that means we get x squared equals negative 1. And what does that tell you about our solutions? We're about to get imaginary solutions, because if you apply the square root property, you take the square root of both sides, and you get x equal plus or minus square root of -1, which means x equals plus or minus I. Now, that means there's, in other words, no real solutions. Now, we are not dealing with calculus and imaginary numbers. So that just tells us there's no critical values. Okay, no critical values. Now I think this is the first time we've actually encountered this issue where we've had a situation where we had no critical values before, but we haven't had the situation where we had no critical values and the domain had discontinuities somewhere in the middle. Like we've had the situation where we've had no critical values, but we had a continuous domain otherwise. Here we don't have a continuous domain. We have discontinuities at -1 and +1. Now remember, we're talking about with the first derivative increasing and decreasing behavior. So the increasing and decreasing behavior can change in an asymptote. So we still have to make our first derivative sign chart because we have to figure out where the function's increasing and decreasing, and that can change at our asymptotes. So basically, we're still going to make our chart, except there's no critical values on it. It's just those asymptotes, -1 and +1. Okay? So let's see what we can come up with over here. Intervals first. So we have -infinity. This is just the domain of the function. Oh, not 0. The domain of the function is -infinity to -1. And then we have -1 to 1. And then we have 1 to infinity. Test points, of course. Is always our second row. -2 works there. 0 is always a nice one, and +2 works there. Then we're going to look at the sign of g prime, the sign of the first derivative. Okay, so notice here, we always try to make this easy on ourselves. The denominator is always positive. Why is it always positive? Because it's a square. It's x squared minus 1 squared. So as long as you're not plugging in -1 or +1, like we're not, it's going to be a positive number. So we don't have to worry about the denominator. All we have to worry about is the numerator. Well, let's see. If we plug in -2, we'll get -2 squared is 4. 4 times -3 is -12, minus 3, I guess that's -15, so I guess negative. Okay. If I plug in 0, I get what? Well, -3, so I guess I get negative again. If I plug in 2, oh, this is kind of weird. If I plug in 2, I get a negative, I get a -15 as well. I am decreasing everywhere. That's kind of interesting. So it is possible that the increasing or decreasing behavior changed at an asymptote, but in this case it didn't. The function's decreasing over its entire domain. So again, results here. I kind of got ahead of the game here. Results decreasing because the derivative is negative. Everywhere decreasing. Interesting. Okay, so we can kind of get the idea of what's happening here. We have two asymptotes, so we know how things have to kind of work around asymptotes. Then we have a function that's decreasing. Interesting. Okay, let's continue. So this is first derivative. Analysis. Okay. Also, so we had no critical values. So let's make that note here. No crit values. And by the way, according to Fermat's theorem, I always keep referencing this, if there's no critical values, what does that tell you about the existence of relative extrema? There are no critical values, there can be no extrema. No local extrema. No minimums, no local minimums, no local maximums. And by the way, since this is not a function that doesn't have a closed domain, we can say there's going to be no extrema at all. There's not going to be any global extrema either, because the only time you can have a global extrema that's not also a local extrema is when that global extrema occurs at the end point of a domain. But here there is no end points of the domain because we have a bunch of open intervals. So there's going to be no extrema of any kind of this function. Okay, so I guess we say we don't have to put that local there. No local extrema. We can say even furthermore, no global extrema. Okay, so that's the first derivative. I guess we can now move on to the second derivative. Okay, so let's look at, I guess just go ahead and calculate g double prime. Oh, let me scoot over just a little bit. Oh, and I erased a little bit too much over here. So g double prime is, okay, another quotient rule. Okay, so let's just see what we come up with here. The derivative of the top is what? Okay, it's negative 6x times the bottom, which is x squared minus 1 squared, minus the derivative of the bottom. Okay, this requires a chain rule. So I have, okay, derivative of x squared minus 1 squared. Outside function, x squared. Inside function, x squared minus 1. Okay, so the derivative of the outside function is 2 times x. I'm just going to put some open parentheses there, because the next step of the chain rule is to put in x squared minus 1. We then multiply by the derivative of x squared, so that's 2x. So our derivative of that function is what? 4x times x squared minus 1. Okay, so I'm going to insert that for the derivative of the denominator. 4x times x squared minus 1 times the numerator. Oh, I'm almost out of room here. Negative 3x squared minus 3, barely squeezed in. So that's the derivative of the numerator times the denominator minus the derivative of the denominator times the plain numerator over the denominator squared. That's the regular denominator. There it is, squared. So on the next line, I'll be raised to the 4th. Okay, now we got some serious cleaning up to do. So g double prime. I guess let's do a bunch of, actually let's do some factoring. Notice that we can factor out an x squared minus 1 from both terms on the numerator. So I can factor out an x squared minus 1, and then it'll leave me some brackets with negative 6 times x squared minus 1 minus 4x times negative 3x squared minus 3. Let me double check that. Factor out an x squared minus 1, so I had negative 6 left over. Oh, good thing I checked it. Negative 6x left over. Negative 6x times x squared minus 1, because we factored one copy out. Then we have negative 4x times negative 3x minus 3 over x squared minus 1. Squared is 4th power. Okay, now let's do a little distributing, and then we'll collect some like terms. So we still have this x squared minus 1. Actually, we can go ahead and cancel, yeah? So let's go ahead and do that. Get rid of that. There's one copy of x squared minus 1 right there. We can cancel and make that 3 copies on the denominator. So x squared minus 1 cubed down there. And now let's just distribute the stuff inside the brackets. Oh, we have what? Negative 6x times x squared. That's negative 6x cubed. Oh, then that's plus 6x. And then we have minus 4x times minus 3x squared. That's going to be plus 12x cubed. 12x cubed, and then we have what? A minus 3 times minus 4x, so plus 12x. Okay? Equals, this took a little more work than I thought it was going to take. On the denominator, x squared minus 1 cubed. And on the top, okay, we have negative 6x cubed and positive 12x cubed. Okay, so that is what? Positive 6x cubed. Then we have 6x plus 12x, that's plus 18x. Okay, cool. Now, what do we do with that derivative, second derivative? So there's g double prime. G double prime. Oh, you know what? I see something that's going to happen here. There is g double prime. I see that I think we're going to have no solutions when we set that equal to 0. But let's verify. I'm just kind of doing that ahead in my head. So of course, the whole point of getting g double prime is to set it equal to 0 and find the critical values of the first derivative. So if we do that, we solve. Actually, I'm gonna reserve that little space for my next chart. So I'll just go down. G double prime equals 0. That's going to be 6x cubed plus 18x over x squared minus 1 cubed equals 0. Well, first of all, notice it has the same discontinuities as the first derivative, same discontinuities as the second derivative. Why? Because, sorry, I didn't say anything wrong, but it was redundant. The second derivative has the same discontinuities as the first derivative, which has the same discontinuities as the original function. Why? Because there's those vertical asymptotes, and there is no slope, and there is no second derivative either. There's no, because there is no slope, there can't be any second derivative either, because there's no function value there. So that makes sense. So we have a quotient. This is the third time in this video I've said this. There's a quotient set equal to 0, so we just set the numerator equal to 0. Notice we can factor out a what? My head work was wrong. There is a solution here. I don't know why I thought what I thought. You can factor out what? A 6 and an x. If you factor out a 6 and an x, that leaves us with what? A x squared plus 3 equals 0. Now we do get a couple non-real solutions because we're going to apply the zero factor theorem and get 6x equals 0 or x squared plus 3 equals 0. Now, obviously, that has a solution, x equals 0. This has no real solutions. Why? For the exact same reason that other one had no real solutions. We're going to subtract 3 from both sides, take the square root. We're going to have solutions negative and positive 3i, imaginary. Okay, so we are not going to have any other critical values, and these are critical values of the first derivative. So critical values of first derivative. Okay. So we can now make our chart. Now here's where you gotta be careful. So we have one critical value. So when you're thinking about making your chart for the second derivative, remember we divide the domain. So the domain is already missing -1 and +1. And now we're going to do the critical value 0 as well. So we have to use this number line when determining our intervals for the chart for our second derivative analysis. So let's see here. Intervals. We have -∞ to -1. Then we have -1 to 0. Then we have -1, 0, not negative. 1, 0 to positive 1, and then we have positive 1 to positive infinity. Oh, let's pick some test points. So -2 works there. Oh, we have between -1 and 0. Now there's not any integers there, but we can do, say, -1/2 and positive 1/2, then positive 2 over there. Now we are going to look at the sign of G double prime. Okay, so G double prime is right there. We can't really say anything too much about making this, reducing this to something very easy at the onset. Why? Well, because the denominator is a cube, so cubes can be negative or positive. So maybe let's just think about this here. I'll keep track of it in my calculator. If you plug in -2 in, that's -8. -8 times 6 is -48. Plus 18 times -2, so that gives you -84 on the top. Divided by, I guess we can think like this way. We're dividing by -2, -2 squared, that's 4 minus 3. 4 minus 3 is positive 3 cubed, so the denominator is positive. So we have a negative numerator, a positive denominator. That gives us overall negative value. Okay. If we plug in -1/2, okay, -1/2 cubed, that's -8, -1/8. So that's 6 divided by -8, plus 18 divided by -2 is another negative number. If you plug in a -1/2 on the denominator, you get -1/2 squared is -1/4. Sorry, positive 1/4. Positive 1/4 minus 1 is -3/4. -3/4 cubed is a negative number. So we have negative numerator, negative denominator, and so we have positive overall result. Okay? Now, if we plug in a positive 1/2, well, the numerator is going to be positive because both terms, there's no negatives involved. So if we plug in a positive 1/2 or a positive 2, the numerator is going to be a positive in both cases. So what's going on with the denominator? Well, on the denominator, if we plug in 1/2, again, you square it, you get 1/4. Minus 1, you get -3/4. Cubed, you get a negative number. So that's going to lead to an overall negative result. But then if we plug in a positive 2, we'll have 2 squared, which is 4, minus 1, 3. The denominator will be positive, so both the numerator and denominator are positive, and so you get a concave up result. So here we got our, we got that plus minus kind of pattern going on, which we've seen a lot. But remember, for the increasing decreasing behavior, we didn't get anything like that. We got all negatives. So this is kind of an interesting example in that regard. Okay, so remember, we're talking about the second derivative being positive or negative, and so our results are going to be where the second derivative was negative. The original function is concave down. So concave down in these two intervals. And then where the second derivative was positive, the original function is concave up. All right. Now, we also need to consider the possibility of inflection points. Inflection points are where we change, first of all, where the function's continuous, and we change from concave up to concave down, or vice versa. Now remember, -1 and +1 are discontinuities. So although it looks like we change from concave down to concave up at -1, -1's an asymptote. It's not an inflection point. Likewise for the change from concave down to concave up at x = 1. Because remember, 1 is a vertical asymptote, so it cannot be an inflection point. There's only one change, and that's a change from concave up to concave down at 0. and 0 is in the domain of the function. So we have one inflection point. It is 0 comma something, but I think we already have seen 0 comma something. 0 comma something, yeah. It's our x-intercept and also our y-intercept. So it turns out that that's also the inflection point, the only inflection point of this function. Okay? Now, lastly, what do we need to do? Oh, limits. We need to take the limit as x goes to infinity. Of the original function, which was what? 3x over x squared minus 1. And we also need to take the limit as x goes to negative infinity of 3x over x squared minus 1. Okay? We can use L'Hopital's rule if you want to. Or we can divide the top and the bottom by both by x squared. That's kind of like the chapter 1 method. But if you use L'Hopital's rule, notice that the top and the bottom are going off. If you're talking about infinity, they're both going. If you're looking at the limit as x goes to infinity, both the numerator and denominator are increasing without bound towards infinity. So it is an infinity over infinity indeterminate form. We could take the numerator derivative and denominator derivative according to L'Hopital's rule, and we get 3 over 2x. Okay? Now, you might not say, well, that doesn't really do a lot of good, but notice what's happening there. We always can stop whenever we get to a limit where the numerator is constant and the denominator is variable. Because if the numerator is constant but the denominator is variable, that means the denominator is growing, and the numerator is staying static, which means the overall fraction must tend towards 0. And notice you get the exact same thing, which is to be expected. You get the exact same thing with the limit as x goes to negative infinity. Because again, if you apply L'Hopital's rule, which you can because it's in negative infinity over positive infinity form, you get 3 over 2x, which again, the denominator is increasing and the denominator is increasing, the numerator is static. It has to tend towards 0. So what do these two things tell us? Remember, if we look at those two limits at infinity and we get a finite solution, this is from chapter 1, if we get a finite solution, this tells us we have a horizontal asymptote. This tells us we have a horizontal asymptote y equals 0. Basically, the x-axis is a horizontal asymptote. Okay, I think we are ready to put it all together. So let me see if I can get OneNote to cooperate and give me a nice set of axes. Yeah. There we go. Nice big set of axes. Okay, now I just need to scroll back over now. Okay, so let's plot the known points first. Okay, so I got a couple. Well, I know for sure 0, 0, that's an inflection point. It's also an x-intercept. So inflection point, x-intercept, and a y-intercept. Okay? Do we have any other points? Okay, we had no extrema. Okay, so just going over here, if we want to just kind of box off our important stuff, we had, the first derivative and the second derivative. That's our really important stuff. And then we had I guess we're also really important, our limits. Okay, and then if we go back up, we have odd symmetry, or odd function, which is origin symmetry. And then we have our intercepts. So x-intercept, y-intercept. I think that's about all their super important information. But I think that means we don't have any other points on our known points on our graph. But we don't really need them, okay? So we do know there's intercepts, though. There's an intercept at +1 and -1. So let's see here. Let's put some like 1, 2, 3, -1, -2, -3. Okay, we have intercepts. Sorry, intercepts. Vertical asymptotes. Did I say intercepts before? Vertical asymptotes. Okay, so there is a vertical asymptote, and here is another one. Okay. Now, we also know there's a horizontal asymptote at the origin. Now, since the horizontal asymptote's at the origin, and well, because it's already black, I'm gonna use a green, or sorry, that's blue. Actually, it doesn't show it very well. Let's use red. That'll show up well. I'm gonna use red to indicate that we have a horizontal asymptote. Okay, we have a horizontal asymptote and we have two vertical asymptotes. Now, let's take into account like how the function has to behave close to asymptotes. And let's also take into account the fact that this function, we know, according to our first derivative analysis, it is decreasing everywhere. That function is decreasing over its entire domain. Okay, so if it's decreasing over its entire domain, think about it this way. We need to get closer and closer to this first vertical asymptote, and we know it's decreasing. So basically, we decrease to that asymptote, and then we decrease between these two asymptotes. And we know that we have to hit that the origin is our intercept. And then we're decreasing afterwards. Okay, so that if you think about what has to happen close to those asymptotes, and then we have to throw in our curvature, so we're concave down when we are to the left of -1, according to our second, oh, sorry, you can't see it because of my picture's in the way. So according to our second derivative analysis, we're concave down to the left of -1. Okay, so that means we're decreasing and concave down. That looks like this. Decreasing and concave down looks like that, which makes sense considering our asymptotes. And then we are, okay, after between -1 and 0, we're decreasing and concave up, which means decreasing and concave up looks like this. Again, which makes sense considering we have asymptotes. And then, okay, we're decreasing everywhere, so between 0 and 1, we're decreasing and concave down, which means we look like this. Again, that makes sense because of these asymptotes we have here. And then lastly, we're decreasing and concave up, which looks like this. So that's what the different parts of our graph are going to look like. Now we just have to put them there. We just have to insert them into the real graph. So let's erase our lines. I always like to start with lines just to show the increasing or decreasing behavior. But note, we're stuck between this horizontal asymptote and the vertical asymptote. So we have a curve that looks like this. Getting closer and closer and closer to that horizontal asymptote. And then we're approaching this vertical asymptote. And again, we have to get super close to it. You never touch it, but get super close to it. Okay, so that's what I said. We have that shape, basically. We have to put it between our asymptotes. And then here, between -1 and 0, we have to start off really close to that asymptote, because that's how asymptotes work. We come down here, we're decreasing, and then we hit that. And again, this is exactly the shape that I said. We're decreasing but concave down. And then afterwards, we're still decreasing, but we change from concave down to concave up. And so we have this shape. We switched to concave. We switched to concave down. And then lastly, we're still decreasing. Now there's no way to come down here and decrease with how asymptotes work. So we know we're starting up here and we're decreasing. We're concave up. Oh, let's not curve too much just yet. So we come down here, we're decreasing and concave up. And we go get closer and closer and closer to that horizontal asymptote, but we never actually touch it. So again, whenever I saw this original function, I wrote these notes 6 months ago. I had no idea what it was going to look like. But with with 41 minutes, minus me talking and giving little extra tidbits here and there, with a not insignificant amount of calculus work and algebraic work, we can get exactly, we can get a very good sketch of all the important features of a graph. Asymptotes, domain, range, inflection points, axes, intercepts, increasing, decreasing behavior, local extrema. We can get all the important